Okay, done.
Thank you. So, well, it's my pleasure to introduce today's speaker, Eva Elduque Laburta from Universidad Autónoma de Madrid. And today she's talking about quasi-projective varieties with orbifolds fundamental groups. And thank you very much, Eva, for accepting our invitation. It's a pleasure for all of us having you here. And please, you may start now.
Right. Thank you, Igor, and thank you to all the organizers for inviting me here. So I just want to warn everyone that when I have the full screen, so I don't see anyone, I don't see the chat. So if at any point you have questions, please make yourself heard because I don't know how to do it otherwise. Or yeah, I guess some organizer can translate the chat if there are questions there.
Don't worry, I will help you.
All right, thank you. Okay, so let's get started. This is what I'm gonna be talking about is doing work with José Ignacio at the University of Zaragoza. And okay, so this is the outline of the talk. First, I'll say some things about the topology of complements of curves, which is gonna be the main object of study in the talk. Then I'll say some things about orbifolds and orbifold fundamental group because, well, this was new to me before starting this project, but we needed it. Then I'll state the main theorem, which again has to do with curve complements whose group is of a certain type. The groups are going to be free products of cyclic groups. So it's going to state necessary conditions on that. Then we'll see that those curves that appear will be fibers of maps to curves. And so we'll talk about addition, deletion theorems, which will have to do with what happens when you add more fibers to your curve or remove more fibers to your curve. How does the fundamental group change? And then we'll end with examples. So let me start by talking about the topology of curve complements in P2, although we'll move on to a more general setting later. So if I have a curve in P2 with r plus 1 irreducible components, Ci, each of the irreducible components is going to be given by an irreducible homogeneous polynomial of degree di. And what we're going to be looking at is the complement of the curve in P2. And the homology of this space is easy. So it's just C to the R, direct product with C mod D, where D is the greatest common divisor of all the degrees of all the curves. So very easy to compute, doesn't have much information about the curve, or it has no information about the singularities of the curve. But on the other hand, the fundamental group is more complicated, but carries more information. So to start, we don't really know the general form or shape that this has, but we know that it is generated by meridians about each of the irreducible components. So, oh, I didn't say, for me, every variety is over the complex numbers. So each of these curves has complex dimension 1, but real dimension 2. It lives in P2, which has real dimension 4. So these curves have codimension 2. So it makes sense to think about loops that go around them. And that's what I mean by meridians. So maybe you need more than one meridian about each of these, but it is generated by meridians nonetheless. And if the curve is smooth, or okay, if it has more than one irreducible components, it's not smooth, but if they intersect transversally, it only has nodal singularities, then the fundamental group is abelian. But in general, if the singularities are more complicated, it won't be abelian, and it carries information about not only the type of singularities, but also the position of the singularities in the curve. So this is a harder invariant to compute than H1. But you can find the presentation of the fundamental group through braid monodromy methods. And if the coefficients of the polynomial are defined over a number field, this is implemented in SAGE. So Miguel Ángel Marco Buzunaris at the University of Zaragoza implemented this, and you just give it the polynomial, the defining polynomial of the curve, and it spits out a presentation of the fundamental group. I think this is amazing. So a presentation of these things can be found, and you can compute many examples and draw your own conjectures from what you're seeing. But again, there's only so much you can do with a presentation. It doesn't tell you what the group is, right? Okay, so here are some examples of fundamental groups that are interesting. So the first example is that of Zariski's sextic. This is an example from the 30s. So if you have an irreducible sextic whose only singularities are 6 cusps, then you have two options for the fundamental group of the complement. It's either this, a free product of two cyclic groups, C mod 2 and C mod 3, if the cusps all lie on a conic, and if the cusps are in general position, then it's abelian. So again, if you see a fundamental group like this, then you know that your curve is going to have complicated singularities that are not nodes, but it could have complicated singularities that are not node and still be abelian. But in this case, what the fundamental group is distinguishing is just the position of the singularities. And more generally, if you want to cook up fundamental groups that look like this free product, so, you know, very much non-abelian, then Oka came up with the following beautiful example in the 70s. So for every pair P and Q coprime with P and Q bigger than 1, what he was able to do was he gave a polynomial which defined the curve of degree P times Q, and such that the fundamental group of the complement was this free product of C mod P and C mod Q. And as we see, the polynomial that he cooked up was, this is a degree P polynomial with to the qth power plus a degree Q polynomial to the pth power. And both polynomials of degree P and Q don't have any common factors and are not powers of any other polynomial. Okay, so in light of those questions, of those examples, the question we asked ourselves was, okay, for which smooth quasi-projective varieties is the fundamental group a free product of cyclic groups? So something like this. We call this an open orbifold fundamental group, and I'll explain why we're calling it that, but we're going to focus on free products of cyclic groups. All right, so I just copied the motivating questions from the previous slide over here.
Excuse me, a question, please, a quick question.
Yeah.
Does the sextic curves that comes with the Oca's example as well?
Say that again. Sorry, I didn't.
Sextic with 6 curves. The previous example that you gave, the sets, it comes from that Oca's example as well. I mean, is it possible to recover that example by Oca's example, or the different ones? Because the Oca's gave you a formula to get the fundamental group has ZQ free product with ZQ. How about that static? Is it comes from that example or what?
I don't actually know. I mean,
did you get my question right?
Yeah.
Okay.
Thank you. It's a good one. So for sure, if you let P equals 2 and Q equals 3 in this example, then you're gonna get a sextic But I don't know if with that one, the only singularities are going to be in the conic, or if they're all cusps. I haven't checked. There are some papers where they actually give explicit equations for Zariski's example, but I don't know if it coincides with OCAS.
Okay, no problem. That's okay. I just wanted to have an idea about the OCAS motivation to get such kind of general curve. Thanks a lot.
Okay. Thank you. All right, so yeah, we have this question for which smooth quasi-projective varieties is the fundamental group of free product of cyclic groups, and I guess some observations. After intersecting with enough generic hyperplanes, that doesn't change the fundamental group, but it takes the dimension down. So you may as well assume that your projective variety is a surface, which is smooth and connected, and that you're removing from it a curve, because from a surface you can remove curves or points, but removing points doesn't affect the fundamental group. So as long as we have a good idea for which curve complements inside smooth connected projective surfaces have such a fundamental group, then well, we won't know in general which smooth quasi-projective varieties, but we know that we can obtain the curve case just by intersecting with generic hyperplanes. And so from now on, I'm just going to talk about curve complements. And I guess something to note is that the original motivation was for curves in P2, not a general smooth connected projective surface. And in those cases, you can't get any free product of cyclic groups appear as a fundamental group. Because okay, if you have something like this, as a fundamental group, then if you abelianize, then you know that the torsion part has to be cyclic. So these PIs have to be pairwise coprime, or it won't. And more so by work of Cogolludo and Lipgover and this paper that I'm talking about, we know that S is at most 2. So if you have a torsion part here, it's of the form CP free product with CQ, like in OCA's example, and maybe you'll have some free part. But that's as far as you can go in P2. Okay. So let me switch gears and talk about orbifolds for a little bit and try to exemplify how these come into play. So, okay, I'm going to define what an orbifold structure on a Riemann surface is. I don't know much about orbifolds in general, so I'm going to restrict to the case that we used here. So what it is really it's a map from your Riemann surface to the positive, well, non-negative integers, but you let almost every point have image 1, and only a finite number of points are going to have image other than 1. So really it's a way to distinguish a finite number of points to which you associate an integer that's not 1, and you're going to think of that integer that you associate to each point multiplicity somehow. So here's the data that's important in such a map. You have some points that go to 0, and you say, okay, there's n plus 1 of them. So the definition of n is this one. You have some points that go to numbers bigger or equal than 2, and those are a finite number of them, so we say there's s of them. And the data that's important is which number they go to. So we just call mi the multiplicity of qi, and collect all that data in a vector with S components. And so really what gives you the orbifold structure is just the union of these two sets, those points, along with the multiplicity. The multiplicities of all of these points, either 0 or bigger or equal than 2. And so for short, we're not going to care about where those special points with higher multiplicity are located within the Riemann surface. We're just going to care how many of those there are and what the multiplicities are. So we'll just use this notation over here to encode this information. There's n+1 points of multiplicity 0, and then there's s points with the multiplicities given by whatever this vector is. Okay, and then one can define the orbifold fundamental group for these things. And it has this definition, which will not give a lot of geometric intuition about what this is doing, but hopefully we can fix that in the next slide. But the definition is just, okay, you take out all the non-standard points, the ones of multiplicity 0 or higher than 2 out of your surface, you compute the fundamental group of that. And then you're going to have loops in that fundamental group that go around the special points. And what you're going to do is those that go around the points that have multiplicity higher or equal than 2, you're going to need to go around them as many times as the multiplicity of that point to make the loop trivial. So this is how the orbifold fundamental group is defined for Riemann surfaces. And I guess we were calling this free product of cyclic groups open orbifold fundamental group because, okay, say you have S, a Riemann surface of genus G. Then you take away all of these points, which are going to be n+1 plus S. And so this group will be a free group of rank 2G plus N plus S. But you're letting each of the generators corresponding to loops around the S points Q1 to QS be such that an mth power of those becomes trivial. So this is how you get this group over here. And so every free product of cyclic groups will appear as an orbifold group of a Riemann surface with an extra orbifold structure, and the open part comes from n bigger or equal than 0. So the points of multiplicity 0, you have to think about like they're not there. It's like they're not in the surface. So that's why we say open. Okay, so let me try to give some intuition about this definition. So I just copied the definition from the previous slide. And let me give an example. So you have the group of mith root of unity acting on the complex numbers on the complex plane. So, and you project to the quotient. So here I drew the complex plane and a fundamental domain of this quotient. So really the quotient would be you take out this triangle thingy and you identify the edges, so you get a cone. So from the point of view of topology, the cone and the complex plane are the same thing. So if you define the orbifold fundamental group just to be the fundamental group of the quotient, you wouldn't be getting information about how this quotient singularity at the origin was attained or anything like that. So what you have to think about here in C, you have a point, the origin, which is gonna have multiplicity. Well, I guess I made this drawing for mi equals 6. So each point in the complex plane has 6 pre-images except for the origin, which only has one. And so you have to think about this point as having multiplicity 6. And so the orbifold fundamental group can be defined using homotopy classes of orbifold loops. And what orbifold loops are, well, these are loops in the quotient. So something like this would be a loop, right? Because this point is the same as this point. But you're going to fix a lift to a path in the surface that you started with. And you consider these up to the action of the group that's acting, in this case, the roots of unity. So like, for example, something like this mu would be the same thing as something like this mu. You see my cursor, right? Or am I just pointing and saying this and...
Yeah, you see.
Okay, thank you. Or it would be the same as this. And so here, the orbifold group of C mod this would be, well, you take out the origin. So same thing that you did here. You're thinking of the origin as a point of multiplicity 6. And then you mod out by a meridian around it to the mth power. And so this would be a meridian around the origin. And the mth power, in this case 6, is saying that, well, to the 6th power, you're really recovering a loop in C, not just the fundamental domain, well, the quotient. So this does give you information about how the quotient singularities were acquired. But for our purposes, we're not going to think of S with its orbifold structure as having any points that are quotient singularities or anything like that. We're just going to use this business to distinguish points and say, no, okay, they're marked and they have multiplicities, and that's going to give us information when we talk about morphisms, which is what I'm going to do next. Okay, so what is an orbifold morphism? We're going to start with a smooth algebraic variety. S is going to be a Riemann surface, and we're going to have a dominant algebraic morphism between the two. And so S is going to be endowed with an orbifold structure with n+1 points of multiplicity 0, and a vector saying what the other multiplicities are that are not 1. And we're going to say that F defines an orbifold morphism into this Riemann surface with whatever orbifold structure we have on it if the multiplicity of the divisor, the pullback divisor over every point of high multiplicity, 2 or more, is a multiple of whatever multiplicity the orbifold structure tells us that that point has. So really, we're going to be interested in what's called maximal orbifold structure. So we're going to say that this orbifold structure is maximal with respect to this morphism if it's not a multiple, it is MI. So what's going to happen is, okay, the image of U, is going to be S minus the points of multiplicity 0. So like the points of multiplicity 0 are what prevents the map from using surjective. So by assigning them multiplicity 0, you're sort of thinking that they're not there. And you're forcing the thing to be surjective. And the multiplicity of the divisor over the special points of high multiplicity will be exactly whatever multiplicity they have by the orbifold structure. And those are all the multiple fibers of the map. So really, the orbifold structure is maximal if it completely tells you the multiplicity of the pullback divisors over every point in the target. And one thing to note is that if F is an orbifold morphism, then, well, you always have a map induced at the level of fundamental groups, but this map is going to factor through the orbifold fundamental group of S. And the idea here is that this thing will be finer than this. So you get closer to the fundamental group of U by looking at the orbifold group of S with whatever maximal orbifold structure. Because it turns out that this map is surjective if the generic fiber of F is connected, which is going to be the case in our setting. And this is the biggest if the orbifold structure is maximal. So really, once you find a dominant algebraic morphism to a Riemann surface, then you put its maximal orbifold structure in it with respect to your morphism, and then you're going to have a surjective map if the generic fibers are connected, and hopefully, I mean, this we know is a free product of cyclic groups, so if on top of that it is injective, we'll have an isomorphism. So looking at algebraic morphisms to a curve seems like a way to try to at least try to understand this problem, or where can these type of groups arise as fundamental groups. All right. So let's see the main theorem. The main theorem gives us necessary conditions for a fundamental group of a curve complement to be a free product of cyclic groups. So again, the setting we were in is we have a smooth projective surface and a inside of it, and we're interested in what happens when the fundamental group of the complement is a free product of cyclic groups. So if this group is infinite, so if it's not a finite cyclic group or the trivial group, then we have the following. There's always going to exist a Riemann surface and a surjective rational map with connected fibers. So by surjective rational, what I mean is that in its maximal domain of definition, it's surjective. Such that, okay, F is going to induce an orbifold morphism from the complement to S with an extra orbifold structure. The extra orbifold structure being the one that makes it maximal with respect to this morphism. But the extra data is going to have to do with a fundamental group. So like the R in the fundamental group is related to the genus and the number of points of multiplicity 0, which is n+1. And the degrees of the torsion factors here are the multiplicities that you find in your orbifold structure. Okay, so you have an orbifold morphism in this case, but it gives you a map between fundamental groups, and this kind of orbifold morphism is going to have connected fibers, so this thing is going to be an isomorphism. So the next question would be, okay, so you've related the complement to an orbifold structure on a Riemann surface, but what about the curve itself? Can we say something about it? And we know that the curve is going to have the following general shape. It's going to be the union of two types of curves, df and dt. F stands for fiber. So df is a union of fibers over the points of multiplicity 0. Well, you have to take the closure, right? Because this is a rational map. And t stands for trivial. So the meridians around the components of dt are all trivial in the fundamental group of the complement. So essentially, the only curves that you can get that give you this fundamental group of the complement are unions of fibers and some other components that don't really matter for the fundamental group, because its meridians are trivial. Okay. So before I give examples to make more sense of this theorem, I wanted to say a few things about the proof in case you also work with the same kind of techniques so that you know that they're involved, but I'm not going to go into the details. So, okay. What we do is we study the characteristic variety of this group. So maybe you've heard this as cohomology jump loci of H1. And so there's these characteristic varieties. It is known that the irreducible components are torsion translated subtori. So that means that they're either tori that go through the identity 1 and C star to the whatever power, or they go through torsion points. So there's this very celebrated paper of Arapura that tells you that if you have a positive dimensional component in the characteristic variety that goes through the origin, then that comes from a morphism to a curve. And Artal, Cogolludo, and Matei generalized that to positive dimensional components that went through not the identity but torsion points. In that case, they also came from morphisms to a curve, but you needed to put an extra orbifold structure on it. And so the fact that this morphism exists, if R is bigger than 1, was a direct consequence of these two papers. But then we have to do more work to prove not just the existence of the morphism, but the fact that this isomorphism holds and the curve is of this form. And if the characteristic variety doesn't have any positive dimensional components, then we couldn't apply the previous work, these two papers, as they were. But what we did is we passed to a cover of the space that had free fundamental group so that we could apply this Artal, Cogolludo to the cover. And then we had to prove that whatever morphism was induced was in fact the Albanese, so that it had functorial properties, and even though that wasn't a cover, it could descend to downstairs to where we started with. So that's roughly the words involved in the proof. So if you work with that, then you know what goes into this, and if not, it doesn't matter, because that's all I'm gonna say. Okay, any questions though? All right. Okay, so let's talk about the main theorem, but in a more down-to-earth way. So, we have the hypothesis is you start with a curve complement whose fundamental group is a free product of cyclic groups, and it's an infinite group. Then what we proved is that the curve was the union of two types of curves. The first one, fibers of a certain map to a certain Riemann surface. And the second one was such that the meridians around the irreducible components of dt were all trivial. And so we have the following observations. The first one is something I already alluded to, which is, okay, if really dt doesn't matter, the fundamental group of x minus d is the same as x minus only the fiber part of d. So essentially, if you want to understand in which cases this happens, you have a fundamental group like this, you can essentially restrict yourself to studying unions of fibers of morphisms to curves. So that's all you have to do. And the fact that there's a C mod mi factor in the fundamental group tells you that the morphism that you get to a curve has a fiber of multiplicity mi, which is not part of the curve itself. Also, you know, I say that a morphism to a Riemann surface of genus G exists, and there's not really, I didn't give you a formula for G because we don't have it. But if X is simply connected, then the only possible surface that you're gonna get is P1. So the original motivation to study this was for curves in P2, and in that case, we know that they're gonna be given by fibers of pencils to P1, which is easier. And in fact, we don't need the infinite assumption here. So the result for P2 is more general and more concrete. And I said before that the trivial part doesn't really matter if you're going to talk about the fundamental group, but for curves in P2, the trivial part is not just that it doesn't matter, it's that it doesn't exist. It's empty. So the curves which give rise to open orbifold fundamental groups are unions of irreducible fibers of maps given by, well, maps from P2 to P1. They're given by two homogeneous polynomials of the same degree. These are very concrete things. And also you know what the number of irreducible components is going to be just by looking at the fundamental group that you start with. R is the rank of the free group appearing here. It's going to have R plus 1 irreducible components. So, you know, if you're hoping for a fundamental group like this, in P2, all you're going to be looking at is fibers of morphisms like this, unions of those. Okay, so let me keep going. What? Here. Okay, so let me say something more concrete about the PQ case. Recall Oka's example from earlier? So with Oka's example, we had this polynomial, which was a degree P polynomial to the Q plus a degree Q polynomial to the P. And the fundamental group of the complement that we got was CP, free product, CQ. And what our theorem says in the P2 case is the following, that Oka's example had to be of this form. There was no other way. So if a curve in P2 satisfies that the fundamental group of its complement is such as Oka's, then the defining polynomial had to be of the form a degree P homogeneous polynomial to the Qth power plus a degree Q homogeneous polynomial to the P power, in the way that the two polynomials have no common factors and such that neither of them is a Kth power of another polynomial. So just of this form. So this is my favorite result of the paper because you start from the fundamental group and you get something about the defining polynomial, which in principle, I mean, they are related, but not in an obvious way. So, yeah, it makes sense that Oka found this polynomial because it couldn't have been much different. So it was a hard example to find. And now let me talk about addition, deletion type results. So let me explain what I mean. Recall the motivating question. We wanted to understand when a curved complement in a smooth projective surface was a free product, had a fundamental group which was a free product of cyclic groups. And by the main theorem, we know that we're only interested in curves which are unions of fibers, of morphisms to a Riemann surface. And so let me introduce some notation. If I have a finite set on the base, on S, on the Riemann surface, I'm gonna denote by XB the complement of the curve that's formed by the fibers over those points, over B. And so the next question is, okay, since you're essentially only looking at fibers in this setting, what happens when you add or delete fibers? So if you add or delete points in the base, then you end up with a curve that has more or less fibers. Is the fundamental group still going to be a free product of cyclic groups? So that's the question now. And the answer is this behaves pretty well generically with respect to addition deletion. So if you have a map as in the main theorem, so surjective, connected fibers, and you have a subset in the Riemann surface with more than one point, and you take a point which is not in that set, but also not in the bifurcation set of F, so the fiber above P is a generic fiber, then the following are equivalent. So you have an orbifold fundamental group here, and you have an orbifold fundamental group if you add the generic fiber. So the two happen at the same time. And in that case, if you have either of these because they're equivalent, the fundamental group of the curve with less fibers is going to be related to the fundamental group of the curve with one more fiber, one more generic fiber, just by this C free factor. So really, this gives you a way to cook up examples. Once you have one example, you just keep adding generic fibers and you'll get, your free part will become larger, but you're still going to be in this open orbifold fundamental group setting. And I should say that 2 implies 1, so this does not need the fiber to be generic. So if you have a curve with open orbifold fundamental group, well, its complement, then you can take out any of the fibers you want. It's still gonna be a free product of cyclic groups. Okay, one thing to note about this proof, apart from, well, the theorem can be applied to cook up examples, but a thing about the proof is that we do not use braid monodromy computations. We just use the fact that we do have a map to S and is generically a fibration because things are algebraic, and with that fibration structure, we don't get a presentation of any fundamental group like this, but we do get enough information about what the presentation is going to look like that we can do this process of adding or deleting fibers in a way that gives us enough information to conclude that whatever result is going to be still a free product of cyclic groups. And I guess, okay, this works if you have a curve whose complement has a fundamental group, which is a free product of cyclic groups, and then you can keep adding generic fibers to your curve, and then you're gonna keep getting these type of curves of fundamental groups. But like, you need a curve to start with. And so what would be the base case here? What if I start with nothing and I just add a generic fiber? Is that gonna work? In general, no, but in P2, yes. So in P2, you can start with nothing, but as long as you have, F is now gonna be a map from P2 to P1. If you take anything that has at least one multiple fiber, so say the pencil is given by two polynomials, you let one of them be a power, then take a generic fiber, and this is going to be an isomorphism where B is empty. So this is just the complement of X, the X minus the curve over P. So in P2, we do have a base case. And as long as the fibers are generic, the fundamental groups are going to be free products of cyclic groups. So Oka's example holds generically once you find the right kind of polynomials. So yeah, I guess that's what I'm gonna say. The consequences. I don't know. Are there questions? I can't see anyone. Okay. So sufficient conditions. If you have FP and FQ defining a pencil from P1 to P2, so satisfying the conditions in the main theorem. So those are FP and FQ are homogeneous polynomials of degree P and Q respectively, greatest common divisor being 1. None of them are a K-power and they don't have common factors. Then, after change of coordinates in P1, you can always assume that the multiple fibers of the pencil lie over these 2 points at most. And our theorem is if you just take R plus 1 generic fibers of something like this, then the fundamental group that you're gonna get is this. It has a free product of rank R, free group of rank R, free product C mod P, free product C mod Q. And so if you just take one generic fiber, you get a curve with the same fundamental group as Oka's example, generically. And moreover, once you have a base case, you can deduce more things. So like, for example, if FP was irreducible, it's not in Oka's example, and you assume that the fundamental group of the complement is abelian. So for example, if it's irreducible and it gives you a smooth curve or only nodal singularities, you have this. And in that case, then you have a base case to apply the addition theorem, right? So if you add to it more generic fibers, so you're gonna add this Z factors. So the fundamental group of the complement will look something like this. Okay. So I guess the moral of the story is generically, once you restrict yourself to getting fibers, you're gonna get this kind of fundamental groups. And just a couple slides with more examples. So in the literature, we found a couple papers that computed fundamental groups with braid monodromy. Computations and the calculations are tedious, but now with our theorem, the proofs are immediate because they're a direct consequence of the main theorem and this addition-deletion business. So the first one is a theorem by Amram and Teicher in 2009, which says, okay, if your pencil is generated by a conic and a double line, a smooth conic, then if you just take R plus 1 smooth conics in that pencil and look at the complement in P2, your fundamental group is going to be of this form. And this is a consequence of our theorem because these are just R plus 1 generic fibers in a pencil. So it has to be this. And And another thing is that Fo has this beautiful paper where he classifies all irreducible maximal thing torus sextics of type 2-3. So what that means is, okay, torus sextic of type 2-3 is the zero of something that looks like this. Degree 2 polynomial to the 3, degree 3 polynomial to the 2, plus in the middle. And tame means that there's some way of decomposing your defining polynomial like this, such that the singularities of your curve lie in the intersection of the conic and the cubic. So Fo classified all of this according to the configuration of the singularities. And he gives 7 families, and Oka and Fo compute the fundamental group of all of these families. And unless you have this configuration of singularities in the other 6 families, the fundamental group is C2 free product C3, like in Zariski sextics. And the reason for that is, well, they do brave monodromy calculations with explicit equations. But for us, we just need to check that whatever curves they give are generic members of the respective pencils generated by the conic and the cubic. So it's easier to check that these are generic members than it is to check to compute the fundamental group. Okay, and lastly, I wanted to say that all of the possible examples do exist and we can produce them. So we have seen examples of curves in P2. Remember, in P2, we could only have something like this, or free. And we've produced these two. But you can also have free groups, right? For example, a bunch of lines going through a point has free fundamental groups, but if we want something a bit more complicated, then you can have a degree D polynomial and a line of multiplicity D, get a pencil, and if you take your line, so as to get trivial fundamental group, and R generic fibers, each of them are going to contribute a free factor of Z, the integers, then your fundamental group is going to be this. Or more generally, if you have something like in Oka's example, but FP and FQ both only have nodal singularities and intersect transversally, so that the union also only has nodal singularities, then you know that the fundamental group of the union is going to be abelian and it's going to have to be the integers. And so if you add R minus 1 generic fibers to it, then you're going to have a free fundamental group as well. And so in B2, all possible examples exist. And we didn't know if in more general surfaces this could happen, if all possible examples exist. But when we put this paper up in the archive the first time, Rodolfo Aguilar contacted us and he pointed us to a result in his thesis where he constructs a surface with a curve such that the complement had a fundamental group of the free part and then several copies of C2s. And he started with a line arrangement and he did some blow-ups so that he could get those multiplicities, and he told us how his method could be generalized to get anything like this. So any open orbifold fundamental group can be seen as the fundamental group of a curved complement in a smooth projective surface by his methods. So I thought that was really interesting. And yeah, that's all I have to say. Thank you very much.